In the next few class sessions, we will be learning how derivatives affect the shape of a graph. We will start by focusing on the effect of the first derivative. We know that the first derivative, f prime at a, gives us the slope of the tangent line to the graph of f at x equals a. Therefore, if f prime is positive, then the tangent line has a positive slope, so the tangent line will rise to the right. Similarly, if f prime is negative, then the tangent line has a negative slope, and so the tangent line will fall to the right. Let's look at the graph of a function y equals f of x. Notice that the function is increasing when x is less than -1, decreasing for values of x between -1 and +1, and then increasing again for x greater than 1. To connect this graph to its derivative, let's draw some tangent lines here and there. Notice that when f is increasing, the tangent lines have positive slope, and so the derivative f prime must be positive here. Similarly, notice that where f is decreasing, the tangent lines have negative slope, and so f prime must be negative here. This gives us a very important result. Let f be a continuous and differentiable function on an interval from a to b. Then, if the derivative f prime is positive on the interval from a to b, then f is increasing on that interval. And if the derivative f prime is negative on the interval from a to b, then f is decreasing on that interval. Let's look at an example. Let's find where the function 2x cubed minus 3x squared minus 12x plus 7 is increasing and decreasing, and then use this information to sketch the graph of f. Recall that in order to determine where f is increasing and decreasing, we need to know where f prime is positive and negative. We need to create something called a sign chart for f prime. Because equality is always easier than inequality, our first step is to find where f prime of x equals 0. Taking the derivative, we see that f prime equals 6x squared minus 6x minus 12. We can pull out the 6 and then factor. So our derivative simplifies to 6 times x plus 1 times x minus 2. And we want to know when this equals 0. Therefore, f prime equals 0 when x is -1 and 2. Our second step is to plot the points where f prime equals 0 on a number line. So, we plot the points -1 and 2. Notice that this breaks up the number line into 3 intervals. We have all of the values less than -1, all numbers between -1 and 2, and all numbers greater than 2. We need to determine whether the derivative f prime is positive or negative on each of these 3 intervals. To do so, we'll use something called test numbers. Now, I need some more room, so I'm going to go to a fresh slide where I'll need the equation of our function, its derivative, and our number line. Recall that we want to pick what we call a test number from each interval and plug it into our derivative f prime. We can use any number we like from each of the 3 intervals of our number line. So we need some number smaller than -1. How about -2? And we need a number between -1 and 2. Let's choose 0. Finally, we need any number greater than 2. How about 3? Notice that there is nothing special about the test numbers I chose. You could have also chosen x equals -5, x equals 1, and x equals 20. The key is just to pick one number from each interval. Sticking with our original choices, we start with x equals -2, and we want to plug this into our derivative to determine whether f prime is positive or negative when x equals -2. Notice that you may evaluate either the factored or the non-factored version of the derivative. It doesn't matter. As our equations become more complicated, it will be easier to work with the factored version, so let's practice that from the start. Evaluating the derivative f prime when x equals -2, we see that f prime of -2 equals 6 times -2 plus 1 times -2 minus 2. Now, we only care about whether this is positive or negative. We do not care about the actual number. We see that 6 is a positive number, -2 plus 1 will be negative, and -2 minus 2 will also be negative. So when we multiply these together, we will have a positive times a negative times a negative. Altogether then, we have a positive value. F prime of -2 is positive. And so, on the interval consisting of numbers smaller than -1, we find that our original function f is increasing. Let's repeat this process with our second test number, x equals 0. Evaluating the derivative at 0, we have 6 times 0 plus 1 times 0 minus 2. The 6 is a positive number. 0 plus 1 will also be positive. 0 minus 2 is negative. Multiplying these together yields a negative number, and so f prime is negative on this middle interval. Therefore, our original function f is decreasing for values of x between -1 and 2. Finally, we'll do this one more time with our final test number of x equals 3. Evaluating the derivative at 3, we have 6 times 3 plus 1 times 3 minus 2, which is a positive number times a positive number times a positive number. In all, f prime of 3 is positive, and so f is increasing on our last interval, the values of x greater than 2. So we found that f is increasing on the intervals -infinity to -1 and 2 to positive infinity, and decreasing on the interval from -1 to 2. Our final task is to sketch the graph of f. Here's a summary of what we found so far. To sketch, note that the x values -1 and 2 were extremely important because those were the values where f had a potential change from increasing to decreasing or vice versa. So first, let's evaluate our original function f at x equals -1 and x equals 2 and plot these points. We see that f of -1 equals 14 and f of 2 equals -13. Let's plot these points. Now, we found that f is increasing when x is less than -1, so we will sketch a function which increases until it gets to -1. Between -1 and 2, we found that our function is decreasing, so we will sketch a function which decreases here, being sure to connect our graph to the points we found. Finally, we found that f increases for values of x larger than 2, and so we will sketch this portion as well, giving us a sketch of the function 2x cubed minus 3x squared minus 12x plus 7. Fantastic! In class, we will look at more complicated functions, but we will see that the process is always the same. First, we find where the derivative f prime equals 0. Then, we plot those values on a number line, dividing the number line into smaller intervals. Pick a test number from each interval and plug these into the derivative f prime to determine whether f prime is positive or negative on each interval. Finally, note that our original function f is increasing when f prime is positive and f is decreasing when f prime is negative. That's all for our introduction. I look forward to seeing you in class.